Welcome to my channel. Alright, today's going beyond the expected episode. It's about unit circle. Alright, I'm just trying to make it interesting. Alright, let's just do some recap before we start. Alright, so let's talk about right angle triangles. Alright, our good old right angle triangle. So we got our three sizes. So right angle is here, the right angle. Yep, so that in a triangle, other than the right angle, we should have two other angle, right? Theta 1 and theta 2. And the longest side on the right angle triangle would be, or the longest side on any triangle would be called the hypotenuse, right? And the other two will be called either adjacent or opposite. Now, the reason why I have not written down the word adjacent and opposite is because they can change, depend on which angle you choose, right? So we got here. Let's say if you choose theta 1, which is this particular angle here. We know that sine theta 1 is equal to opposite over hypotenuse. So with respect to theta 1, B, the letter B here, or the side B here, would be your opposite, right? Opposite to the hypotenuse, opposite to the angle, right? So sine theta is equal to opposite over hypotenuse. Next one. Cos theta. Now cos theta, if we are using theta 1, would be equal to A over hypotenuse. In this case, A will be the adjacent side. Well, if you look at the diagram, it makes sense as well. The side A here is literally adjacent to the angle theta 1. Hence the name adjacent. Right. So cos theta 1 is equal to adjacent or side A over hypotenuse. Right, giving us the last, which will be tan. So tan theta, if we're going with this particular angle, theta 1, will be equal to B over A. Now, just then we mentioned B is the opposite with respect to theta 1, and A is the adjacent with respect to theta 1. So tan theta would equal to opposite over adjacent. Okay, cool. So far so good. And in here, if you choose theta 2 as your angle, so some things would change a bit. Not the hypotenuse, but the opposite and adjacent. Alright, so if you choose theta 2 as your angle, sine theta 2, right, would be equal to A over hypotenuse. Because when we're looking from the angle from theta 2, literally looking from the angle of theta 2, what is opposite is side A, right? Which side is opposite to theta 2? Side A. Hence, that side, so side A has changed from theta from adjacent with respect to theta 1 to opposite with respect to theta 2. Right? So that's the reason I did not write down the names, because they can change. Alright, so cos theta 2, cos theta 2 is equal to B over hypotenuse. Simply because the side B, the relationship between side B and theta 2 is an adjacent relationship, right? Meaning side B is adjacent to theta 2. So therefore, cos theta is equal to B over hypotenuse, which is adjacent over hypotenuse. Last but not least, tan theta. So if we choose theta 2 as our angle, tan theta 2 will be equal to A over B, which is opposite over adjacent. Right, so we can literally write something down now. So we got, we haven't used black yet. So we got tan theta equal to opposite over adjacent, right? And then we got cos theta equal to adjacent over hypotenuse, and sine theta equal to opposite over hypotenuse. Now I know this should be common sense, right? If you are in year 11 or year 12, but hey, no harm going through the basic just to make sure everybody's on the same level. Okay, another basic thing I want to go over again would be our Pythagoras Theorem. All right, Pythagoras Theorem. You know, when it comes to right angle triangle, how could you miss Pythagoras Theorem? So in Pythagoras Theorem, well, what Pythagoras come up with, his theorem, right, is that if we square the side A and add the square of sine B, we actually get the square of sine C. Now, normally that's where the teacher will stop, right? So now people and the student will just go, okay, A squared plus B squared equals C squared. Great. Now I'm not saying that is wrong, but come on, we need some visuals. You know, math is all about visual. Yeah, seeing it is to believe it, right? So what we have down there, what I have prepared is no copyright infringement intended. All right, so we got here. So this is literally what it means, right? So I got a triangle here. Oops, no, there's a little dot. Yes, got it. All right. So there's literally a triangle here, a right angle triangle. I'm trying my best to draw it as as 9 degrees as possible. So we literally so when we talk about A square or B square, we are literally creating a square, right? Yeah, A square means A times A. And if that's what it means, we will create a square with a side length of A, right? So there we go. This is a square with a side length of A, which is A square. So the area of it is A square. All right. And on the other side, we got B. We got another square created by the length of B. So this square will have a side length of B. And the area of this particular square will be B square. And what Pythagoras really trying to say is the area of this black square over here plus the area of this red square over here is equal to the area of this blue square over here. And that is what Pythagoras trying to prove. Well, that's what Pythagoras has proven. All right. So I know this might seem to be trivia, you know, I think many people say, oh, I know this already, but hey, be considerate for those people that might not have a chance to see it, or at least see it this way, okay? So make sure, I'm just making sure the playground is leveled, you know, everybody is on the same level. Okie dokie, so let's get down to business. Unit square. Okay, so unit square. Now, what is unit square? Well, the word unit. Sorry, not a unit square. Sorry, my bad. It's not a square. Unit circle. Unit circle. Now, the unit circle, what the unit means that the measurement of this particular circle is down to its most basic, or most simplest form. By that, I mean the radius of this particular circle, so we see this particular line here, the radius of this particular circle is 1. Oops, so let me write it better. So the radius is equal to 1. So this circle is the most basic one, right? Anything beyond any size, any other circle beyond this one is just a factor, or just a proportion, or just a scalar to this particular circle, right? So I mean, you can draw a big circle. Let's say you can draw a circle with 100, with r equal to 100, right? But that is literally just literally a proportion, 1 to 100, right? So I can shrink the circle with a radius of 100 times to get back to the most basic circle with a radius of 1, right? So the 100 just becomes a factor or a scalar, something that, or it's just a proportion. So the unit circle means when the circle is in its most simplest form, right? All right. After we get that bit over, so since this circle has a radius of 1, I want to label all 4 sizes first on a Cartesian plane. All right. So on a Cartesian plane with a unit circle, this particular point here, starting from let's say from our 3 o'clock direction, our 3 o'clock position, is where we begin. Right? A lot of people don't know this, right? We actually begin the journey here, the journey through unit circle here. So we start over at the 3 o'clock position. We go anti-clockwise. So we go back and then we travel to the 12 o'clock position, 9 o'clock position, and 6 o'clock position, and coming back to the 3 o'clock position, right? To form a circle, 360 degrees. So we always start at the 3 o'clock position, all right? Going anti-clockwise. And when you come back one round, you would have traveled 360 degrees on the unit circle. Okay. So let's label this extremity, this point on the edge of the circle with the Cartesian plane. So at this point here, we obviously, since we know the radius is equal to 1, so our x coordinate here at this point will be 1, and the y coordinate here will be 0. Right? Makes sense? At 12 o'clock position, so our radius is 1, but now the radius is in the y-axis direction. So our y is actually 1, and then our x has a coordinate of 0. All right. When it travel down to the 9 o'clock position, we know that, or hopefully we know that the Cartesian plane, all right, the traditional Cartesian plane is negative. Right, the x is negative on this side. So on the left hand side, no, let's not put it left hand side. So we should go, let me see. So the y is positive here. Y equal positive here. X is positive here. Right? And therefore, on the Cartesian plane, x will be negative here. And last but not least, y will be negative here. Right? And that is just basic Cartesian plane knowledge, or what do you call it? Common sense. But then again, no, I shouldn't call that common sense because nothing is common. Okay. So x will be on the left hand side of the Cartesian plane will be negative. So since our radius is 1, it would have reached out to the negative side by 1. So our x coordinate at the 9 o'clock position would be -1, and the y coordinate would be 0 because it's right on the x-axis. All right, and then when at the 6 o'clock position, the x coordinate will be 0 because it's right on the y-axis, and our y coordinate will be -1 because our radius is 1 and it's stretching out to the bottom where y is negative. All right. After we got that bit done, let's talk about the angle. Now, obviously, so far where people would be used to using theta to represent angle, correct? And there's nothing wrong with that. And we know that one full revolution is 360 degrees, right? 360 theta equals 360. But I hope you do know. I hope you do know that 360 is a man-made number. What I meant by that is, back in the, I believe the city is called Babylon. Back in the time of Babylon, when it was still a country or a civilization, they come up with 360 degrees represent a circle, 60 minutes represent an hour, 60 seconds represent a minute, and 24 hours represent a day. They come up with that simply because those numbers is able to divide it by 6. Now, obviously, there's a very interesting story behind the choice of numbers. Why they use 6 or something that can be divided by 6 to represent time, angles, and other things. And we will talk about that in another episode of Going Beyond the Expected. Definitely, I will make that happen. But what I'm trying to say is theta is a man-made number, or at least 360 degree is a man-made number to represent a circle. And mathematicians don't really like that. We don't really like that. How do you know one's circle or one full revolution is 360 degree? Because we just said it. We can, if the people in Babylon was using, let's say, 100, all right, they can only use 100 to represent a circle. Then we will have 25. We will have a 0 here, 25 here, 50 here, 75 here, and 100 back. Right. So the number made by the Babylonian is just they just invented that number. So mathematician needs something else. Needs something that doesn't really change. It doesn't really change, and then there's where they discovered to use pi, right? Because pi represent a single segment, or radian. Sorry, no, they use radian, not pi. They use radian. Radian we use so degree we use a little circle, right, to represent degree. And in radian, we use a little c to represent radian. And now that is just means the curve of the circle. So every bit of so if we divided the circle into like, like a pieces, every piece of it is a radian. So every curve is a radian. So that is a radian. Right? So that's what radian is. And that is more definite than just putting a number like 6 or 10. Because we can find, well, thanks to a lot of scientists or mathematicians, we were able to actually get down to very close to what one radian is. And so therefore, in unit circle, they don't really like to use theta. They would prefer to use the angle unit of radian to represent angles. Now, that's all right. All we have to do is just have to do a simple conversion of the unit. All right. So we know in the unit radian, pi is equal to 180 degree. Okay, pi is equal to 180 degree. That means the half of the circle, so from one side of the circle went to the other opposite side, that's 180 degree, correct? And that can be represented by pi in radian. All right, using that as as a base, we can come up with a conversion formula. So let's say if we have 60 degree, all right, and we can convert that from degree to radian simply by multiplying by pi over 180. Right. The reason why we do that is because pi and 180 is the same thing. All right, they represent the same value, 180 degree, and pi is just a radian, a radian unit for angle, and they represent the same angle. So something, if something over something, given that something is the same, right? If the same thing divided by itself, we equal to 1, and the good thing about that is it doesn't really change the values of anything else. So the reason why we can do that is if we use 60 to multiply by 1, right? It doesn't change the value of 60. So it still be represent as the correct measurement of what we're starting with. But now, pay attention. It's just that the unit of the angle will change. All right. So like I said before, radian is a unit of C, right? And pi, and 100 and degree is theta or degree is in the unit of degree, right? Now, a lot of teachers don't actually teach their student about this, which I think is horrible, which I think they should. All right, it's about when you're doing calculation. All right, obviously the number changes, right? When you do the calculation, 5 plus 3 becomes 8, or 7 times 4 is 28. All right, so it's not only the number that is changing, the unit also change. All right, so when you multiply 60 times pi over 180, you get this 60 pi c over 180. Right? Correct? So the degree here, the unit degree here actually get cancels. And that leaving you to 60 over 180 pi. Right? And 60 over 180 is just 1 over 3. So it's literally pi over 3. Correct? But now the only since the degree unit is gone, the 1 over 3 is just a ratio, and whatever unit left is just the radian is left here. So that's how we convert it. Once we do the calculation by multiplying a degree with pi over 180, the degree unit actually got cancelled out. Okay, and what we're left with is the radian unit, and that's why we can convert a degree into radian, because that's the only unit left. Likewise, you can do it the other way. So let's say we got pi on 4. All right, so we want to convert pi on 4 back to degree, right? So we have to multiply by what? Yep, I heard some of you say it. Deep down, I heard some of you say it. Is 180 over pi. Why? Because we can cancel the unit in this way, right? So 180 over pi is the same as pi over 180, right? It doesn't change. The value is still 1. It doesn't change any value. It doesn't change anything. But now the unit is opposite. Degree is on the top, and radians at the bottom. And now because we're trying to convert radian back to degree, we should make the radian, the unit radian cancels. Right? So we go cancel and cancel. And we just literally are leaving with 180 degree divided by 4. Now, divided by 4 is just a ratio, right? So our degree is the same. So the only unit we remain is degree. So 180 divided by 4 would be 45 degree. So that's why when you want to convert from degree to radian, you multiply by pi over 180. And when you want to convert from radian to degree, you multiply by 180 over pi. Simply because they can cancel the unit that we're trying to convert from. Yeah? So I see a lot of teachers just go, oh, you can just do this, times that, and time when you want to convert the other way, you times the other way. But not many of them actually go through why. Okay, so the reason why is because of the unit being cancelled out. Whew. All right. So after we get this all out of the way, we can start looking at angles right now. Okay, so we can start looking at different angles. And we are at 25 minutes already, so let's say we take a little break, shall we? And then we come back with part 2.